Someone left this urgent comment in one of my videos. I need a calculus person immediately to help me differentiate this. And I am the right person for this job because I am teaching a multivariable calculus class right now, and that looks like a parametric curve. And by differentiating a parametric curve, what we mean is finding all the tangent vectors at every point. So let's do exactly that. This is the curve that they want me to differentiate to find tangent vectors of. And it's a little sketchy. So let me first try to find a model that looks like this, and then I'll take derivatives of that. It looks like the curve starts right there, and then it goes clockwise, doing cycles along the way as it spirals towards the origin. This is a job for epicycles. Let's start parametrizing a circle that is going from the North Pole and clockwise, and that is what this curve right here does for you. Here I've added one epicycle, so it's doing a lot of loops as it goes around the big loop. But I need the path to spiral towards the origin, so I'm going to multiply the entire vector by a factor that decreases with time. I'm going to try first to multiply by 1 over t plus 1. But then the radius decreases too fast and it doesn't look like what we want. So I want to multiply by something that goes to 0 but slower than this. So I'm going to multiply instead by 1 over log of t plus 1 plus 1. And this one sort of looks right, but it goes to 0 very slowly. So let's increase the interval of time to do more loops. And this looks better, but this function goes to 0 so slowly that we're never going to be able to fill in the center. So I need something in between. So I'm going to multiply instead by 1 over the square root of t plus 1. Now that looks better. Let's clean up a little bit. This looks much better, but I still need to fill in the center. So let me increase the time interval to 1000. And this looks great, but at the beginning of time, it was decreasing too fast. So let me start at a different time so that we get something closer to what we want. So when we start at time equals 6, I get something that is reasonably close to the image they gave me. For reference, this is what I was trying to model. So now that we have a parametric formula for this curve, I can take the x-coordinate and take the derivative with respect to time, and that's what I get. Take the y-coordinate, take the derivative with respect to time, and that's what I get. So those are the coordinates of the differentiation of this curve, so the coordinates of the tangent vector at any given point at any given time t.